Every ultrasound probe faces a specific physical task. It must project high-frequency sound waves into the body while simultaneously listening for microscopic echoes returning. B-mode imaging functions by converting acoustic pressure into electrical data. Returning echoes generate measurable voltages, which the system displays as points of brightness on a monitor. This continuous translation is made possible by the piezoelectric effect. When an electrical voltage is applied to a piezoelectric crystal, the material mechanically distorts and vibrates, producing a sound wave. This process is reversible. When returning acoustic echoes strike the crystal, the resulting vibration generates an electrical voltage directly proportional to the intensity of the pressure change. Every clinical ultrasound image is bounded by the physical limitations and precise engineering of this crystalline material. Efficiently maximizing acoustic output requires the transducer design to leverage the physics of wave interference. This is constructive interference. When two sound waves cross in the exact same phase, they combine and reinforce one another, compounding their amplitude. If those waves cross in different phases, however, they cancel each other out and ruin the signal. Transducer design relies on natural or resonant frequency to ensure these waves stack constructively. A transducer produces maximum output when the acoustic wavelength is exactly twice the thickness of the piezoelectric disc. Here, exactly 1/2 of the wave fits within the disc. As the material pulses, it reinforces the emitted waves because this specific thickness forces them exactly in phase. This means a sonographer's choice of frequency is hard-coded into the hardware. The crystals are physically cut to exactly half the thickness of their target wavelength. Generating a strong wave is only the first step. A crystal cannot listen for returning echoes if it continues to ring after the initial electrical pulse. Clinical imaging requires discrete, isolated sound pulses to establish distinct spatial resolution between tissue boundaries. The mechanical coefficient, or Q value, reflects how quickly the crystal's vibration is dampened after the pulse. A material with a high Q value has light dampening. Once struck, the crystal vibrates for a long time and the pulse persists. By contrast, a low Q value material uses heavy dampening to stop the vibration rapidly, resulting in a very short pulse duration. While musical instruments are designed to sustain a note, clinical ultrasound requires low Q value engineering to create the sharp, brief pulses necessary to listen for echoes. Sound waves travel through human soft tissue at a fixed average velocity of exactly 1,500 meters per second. Creating a single scan line requires a specific chronological sequence. The transducer transmits the pulse, waits for it to reach the target, and waits for the echo to return before generating the next pulse. This round trip is governed by the distance equation. Distance equals time times velocity times 0.5. The frame repeat rate is the pulse repetition frequency, or PRF, calculated by multiplying frame rate by scan lines per frame. The primary constraint on PRF is the listen phase. The transducer waits for an echo from the deepest target tissue to return. This dictates the depth of view. Depth equals 0.5 times the sound velocity divided by the PRF. Because the speed of sound is constant, imaging deeper anatomical structures necessitates a longer listen phase. Similarly, increasing the number of scan lines to gain more detail requires more pulses per frame, which also forces a lower PRF. This creates a fixed clinical trade-off. Since the velocity of sound in tissue is rigid, a sonographer cannot maximize depth, frame rate, and line density simultaneously. Extending one of these variables mathematically starves the other two. A single transducer's beam begins parallel in a useful near field, then diverges into an unusable far field. This near field equals the transducer diameter squared, divided by 4 times the wavelength. Widening the crystal extends this section, but at a cost. Simply increasing the width of a single transducer is impractical. It severely reduces spatial resolution and makes the probe too large for clinical use. Modern probes bypass these single crystal limits using a stepped linear array. This design uses many tiny transducers placed in a row. They are activated in synchronized groups to mimic a wide beam, then deactivated as the next adjacent group fires, sweeping the beam across the array laterally. This geometry enables electronic focusing, which allows the system to manipulate the wavefront's convergence. By firing the outermost crystals first, then the inner and the innermost last, the wavefront curves. The sound waves converge into a tight focal point at a targeted depth below. Linear array sequencing frees the system from the geometric limits of a single crystal, providing high-resolution, dynamic focal control without sacrificing physical maneuverability. Every diagnostic B-mode image represents a real-time translation of hard mechanical constraints into electrical data. The physical thickness of the cut crystal establishes the operating wavelength, and heavy backing dampening isolates the resulting pulse. The rigid 1500 meter per second speed limit of human tissue dictates the mathematical relationship between target depth and frame rate. Finally, the sequenced electronic timing across a multi-crystal array allows for precise near-field mapping and focal depth control. Mastering these bedrock physical principles separates basic operation from advanced clinical mastery. Understanding the physics allows the user to actively manipulate the limits of the beam to optimize diagnostic yield.